Next, let's take our k-means clustering example that we used earlier in this course and solve it this time using Spark and MLlib, and you'll see it's just as easy, maybe even easier. All right, let's look at another example of using Spark and MLlib, and this time we're going to look at k-means clustering. And just like we did with decision trees, we're going to take the same example that we did using scikit-learn, and we're going to do it in Spark instead, so it can actually scale up to a massive data set. So again, I've made sure to close out of everything else here, and I'm going to go into my course materials and open up the Spark k-means Python script, and let's study what's going on in here. All right. So again, some boilerplate stuff. We're going to import the k-means package from the clustering MLlib package. We are going to import array and random from NumPy because, again, we're free to use whatever we want. This is a Python script at the end of the day. And MLlib often does require NumPy arrays as input. We're going to import the square root function and the usual boilerplate stuff. We need sparkconf and sparkcontext pretty much every time from PySpark. We're also going to import the scale function from scikit-learn. So again, okay to use scikit-learn as long as you make sure it's installed on every machine that you're going to be running this job on. And also don't assume that scikit-learn will magically scale itself up just because you're running it on Spark. But since I'm only using it for the scaling function, it's okay. All right, let's go ahead and set things up. So I'm going to set a global variable k to 5. So I'm going to run k-means clustering in this example with a k of 5 with 5 different clusters. And I'm going to go ahead and set up a local Spark conf, just running on my own desktop. I'm going to set the name of my application to Spark k-means and create a Spark context object that I can then use to create RDDs that run on my local machine. We'll skip past this function for now and go to the first line of code that gets run. First thing we're going to do is create an RDD by parallelizing in some fake data that I'm creating. And that's what this create clustered data function does. Basically, I'm telling it to create 100 data points clustered around k centroids. And this is pretty much identical to the code that we looked at when we played with k-means clustering earlier in the course. So if you want a refresher, go ahead and go back and look at that lecture. But basically, what we're going to do is create a bunch of random centroids around which we normally distribute some age and income data. So what we're doing is trying to cluster people based on their age and income, and we're fabricating some data points to do that. All right, so that returns a NumPy array of our fake data. Now the other thing we're doing, so once that result comes back from create cluster data, I'm calling scale on it. And that will ensure that my ages and incomes are on comparable scales. Now remember my lecture saying you have to remember about data normalization. This is one of those examples where it is important. So we are normalizing that data with scale so that we get good results from k-means. And finally, we parallelize the resulting list of arrays into an RDD using parallelize. So now our data RDD contains all of our fake data. All we have to do, this is even easier than a decision tree, call k-means.train on our training data. Pass in the number of clusters we want, our k value, a couple of parameters that put an upper bound on how much processing it's going to do. We're going to tell it to use the default initialization mode of k-means, where we just randomly pick our initial centroids for our clusters before we start iterating on them. And back comes a model that we can use. We're going to call that cluster. All right, now we can play with that. So let's start by printing out the cluster assignments for each one of our points. So we're going to take our original data and map it, that is transform it using this lambda function. This function is just going to transform each point into the cluster number that is predicted from our model. Okay? So again, we're just taking our RDD of data points. We're calling clusters.predict to figure out which cluster our k-means model is assigning them to. And we're just going to put the results in our result RDD. Now, one thing I want to point out here is this cache call here. So an important thing when you're doing Spark is that anytime you're going to call more than one action on an RDD, it's important to cache it first. Because remember, when you call an action on an RDD, Spark goes off and figures out the DAG for it and how to optimally get to that result. And it will go off and actually execute everything to get that result. So if I call two different actions on the same RDD, it will actually end up evaluating that RDD twice. And if you want to avoid all that extra work, you can cache your RDD in order to make sure that it does not recompute it more than once. So by doing that, we make sure these two subsequent operations do the right thing. So in order to get an actual result out of this result RDD, what we're going to do is use count by value. And what that will do is give us back an RDD that has how many points are in each cluster. Okay? So remember, result RDD has mapped every individual point to the cluster it ended up with. So now we can use count by value to just count up how many values we see for each given cluster ID. And we can print that list out. And we can actually look at the raw results of that RDD as well by calling collect on it, and that will give me back every single points cluster assignment, and we can print out all of them. Now, how do we measure how good our clusters are? Well, one metric for that is called the within set sum of squared errors. Wow, that sounds fancy. It's such a big term, we need an abbreviation for it, WSSSE. All it is, we'd look at the distance from each point to its centroid, the final centroid in each cluster, take the square of that error and sum it up for the entire data set. Okay? So it's just a measure of how far apart each point is from its centroid. Obviously, you know, if there's a lot of error in our model, then they will tend to be far apart from the centroids. That might imply that we need a higher value of k, for example. So we will go ahead and compute that value and print it out. Now to do that, we define this error function that computes the squared error for each point. It just takes the distance from the point to the centroid center of each cluster and sums it up. So to do that, we are taking our source data, calling that lambda function on it that actually computes the error from each centroid center point. And then we can chain different operations together here. So we're calling map to first compute the error for each point, okay? And then to get a final total that represents the entire data set, we're calling reduce on that result. So we're doing data.map to compute the error for each point, and then .reduce to take all of those errors and add them all together. And that's what this little reduce lambda function does. This is basically a fancy way of saying I want you to add up everything in this RDD into one final result, okay? So reduce will take the entire RDD, two things at a time, and combine them together using whatever function you provide. So the function I'm providing here is take the two rows that I'm combining together and just add them up. Okay? And if we do that throughout every entry of the RDD, we end up with a final summed up total. It might seem like a little bit of a convoluted way to just sum up a bunch of values, but by doing it this way, we are able to make sure that we can actually distribute this operation if we need to. You know, we could actually end up computing the sum of this piece of the data over here on this machine and a sum of a different piece over on this other machine, and then take those two sums and combine them together into a final result, right? So you see how that works? This reduce function is saying, how do I take any two values, you know, intermediate results from this operation and combine them together? All right, so again, feel free to take a moment and stare at this a little bit longer if you want it to sink in. Nothing really fancy going on here, but there are a few important points. We introduced the use of cache if you want to make sure that you don't do unnecessary recomputations on an RDD that you're going to use more than once. We introduced the use of the reduce function, and we have a couple of interesting mapper functions as well here. So there's a lot to learn from in this example. But at the end of the day, it will just do k-means clustering, so let's go ahead and run it. Again, go to the Tools menu, Canopy command prompt, and type in spark-submit spark-k-means.py, and off it will go. It worked. Awesome. So remember, the output that we asked for was first of all a count of how many points ended up in each cluster. So this is telling us that cluster 0 had 21 points in it, cluster 1 had 20 points in it, so on and so forth. Ended up pretty evenly distributed, so that's a good sign. And then we also printed out the cluster assignments for each individual point. And if you remember, the original data that fabricated this data did it sequentially. So it's actually a good thing that you see all the 3s together and all the 1s together and all the 4s together. You know, it started to get a little bit confused with the 0s and 2s, but by and large, it seems to have done a pretty good job of uncovering the clusters that we created the data with originally. And finally, we computed the WSSSE metric. Came out to 19.97 in this example. So if you want to play around with this a little bit, I encourage you to do so. You can see what happens to that error metric as you increase or decrease the values of k and think about why that may be. You can also experiment with what happens if you don't normalize all the data. Does that actually affect your results in a meaningful way? Is that actually an important thing to do? And you can also experiment with the max iterations and run parameters up here on the model itself and get a good feel of what that actually does to the final results and how important it is. So feel free to mess around with it and experiment away. That's k-means clustering, done with MLlib and Spark in a scalable manner. Very cool stuff. There you have it, k-means clustering done on Spark and MLlib. Pretty simple stuff, and the beauty of it is you could actually throw a large, massive real data set at it, and if you were to run that on a cluster, it would actually carve it up for you and distribute all that processing automatically, and it would still work just fine. Pretty awesome. Let's move on to an even cooler example.